Hey there, guys. This is the AP Physics 1 screencast for work. I'm going to try to get this all into one video, so here we go. First of all, let's take a look at, before we get into this, I want you to watch this video right here, Boson Video Work and Energy. And you also find these are some of the other resources that I've given you for this particular lesson, and that's what the work and energy video is going to look like. So on to the slides. Okay, so we previously looked at energy, and I told you that there was going to be a relationship between energy and work. We're really going to dive into that a little bit more here. Dot product and also work energy relations. So the first part of this, we're just going to learn how to calculate work and solve some problems. We're also going to look at this part right here where we have an equation that's going to relate work and energy and solve problems with that as well. Okay, so work is just, you've probably seen this definition before in previous science classes. Work is equal to force times distance. Well, that is true, a very simple definition, as long as the force applied and the displacement are in the same direction. Of course, that's not always the case. You might have other forces at work or whatever. So we say the dot product. All this means for us is that we're going to add a cosine theta at the end of our formula. What that's going to allow us to do is to account for the differences here. We're going to go back to trig like we first learned in the vectors unit. Basically, this cosine theta is going to allow us to calculate the collinear portion. So if I'm looking at force and displacement here for this object, I'm applying a force like this, but this object is moving like this. So obviously that means there must be something else going on, some other forces that are acting, but all we want to know is the work due to this particular force. So the cosine theta is going to allow us to find, if I kind of follow the cursor there, this is my vector, and then I've got kind of the y component there, and then I've got the x component, so to speak. It's this component that I'm interested in. That's going to be the work only due to this force. So adding the cosine theta is going to allow you to solve for that. Really quickly, so if I'm exerting a force on a book, we're going to look at several different scenarios here. So if I exert 15 newtons but I have 0 displacement, what do you think the work is going to be on that? It's going to be 0 joules because it's force times displacement. Even though I'm doing work on this, I'm not moving it. Maybe this is a really heavy book. And 15 newtons just doesn't budge it, doesn't overcome the static friction. But if I apply 15 newtons and it moves 1 meter, that's in the same direction, so 15 times 1 just gives you 15 joules. Now, on the contrary, if we have 15 newtons being applied, but we have 1 meter displacement in the opposite direction, like say a book is sliding across the table and you have 15 newtons of friction acting against it, you would say that that is a negative 15. Yes, we can have a negative here. The negative work just means it's moving in the opposite way of the displacement. And then 15 times 2, it's going to be 30. 30 times 2, it's going to be 60, both collinear. But we have a problem here. 15 newtons up, but 2 meters right. Those form a perpendicular, so what do you think the answer to this is going to be? Did you say 0? It is. Because there is no collinear component of the force and the displacement. They are completely perpendicular, meaning there's nothing there. So this 2 meters of displacement has absolutely nothing to do with this 15 Newton force, and therefore we are doing 0 joules of work. And then 5 newtons times 0.5, we just take half of that, 2.5 joules. But right here, this is a 45-degree angle, by the way. So if I want to solve for this, I'm just going to say 5.3 newtons times 0.5 meters times cosine 45. And when I do that, I get, I think it's like 1.87, so it's 1.9 joules there. So that 1.9 joules of work is if I take this force, that is the collinear portion of that displacement that gives me that. And then finally, if I'm exerting 0 newtons, but I'm still having displacement, again, that's going to be 0 because work depends on force and displacement there. So some key ideas there. Work is scalar. It's not directional. It can be positive, negative. And then also, because energy is required to do work, you're always going to have a corresponding change in energy. That leads us to the next section, work-energy relations, and that's the last part we're looking at. So if work is done, we're going to have some kind of energy transfer or transformation, meaning it's either going to transfer from one object to another, or it's going to transform from, say, potential to kinetic energy. So if a force does positive work, zero work, or negative work on an object, what are going to be the results of that? So if I'm doing positive work, say I have a ball and I'm rolling it across the table, I have increased its speed. And if I've increased its speed, think back to the definition of kinetic energy, 1/2 mv squared. That means I'm going to increase its energy. Increase speed, increase energy. If I'm doing zero work on it, I'm not changing anything, so that's no change in energy as well. And so, yeah, it kind of follows it. Negative work, like say a frictional force, that's going to decrease in energy because you're decreasing the speed. And what this all leads to is the amount of work will precisely equal the amount of change in energy, and that leads us to a very important physics formula here. Net work is equal to your change in kinetic energy. And that change in kinetic energy is just defined as your final minus your initial there. It's important to know what's going into our net work here. If you imagine a car going down the road, well, and it's accelerating. Well, it's accelerating because the engine's putting out power, right? And it's accelerating because the engine is putting out enough power to overcome any air resistance or anything else that would be causing that car to slow down. Because if you let off the gas, you're going to coast to a stop because of air resistance, frictional forces, whatever. But if the car is accelerating, then it's overcoming that. So that net work there would be the work of the engine minus those frictional forces there. Going to get a little bit of a sidetrack that's going to make sense here in the next slide. We're going to look at conservative and non-conservative forces here. A conservative force is basically just, we can only determine potential energy if we're talking a conservative force. Like if I'm holding a ball up above a table, I can measure the height, I drop that ball, that potential energy becomes kinetic energy. That only depends on a change in position, in other words, the displacement. A non-conservative force, though, depends upon a path. If you're looking at friction of a car going, well, that friction is going to be there regardless of displacement. It's going to depend on the path. So that's what we're looking at here. It's those non-conservative forces that are going to be important for what we're looking at from here on out. Potential energy and work. Potential energy just means the potential for work to be done, because we have that equivalency between energy and work that we just talked about. If we find the change in potential energy, it can help us to find the work of a particular conservative force. Because remember, if you find the change in potential energy, then you'll know the change in the kinetic energy, because remember, Ke1 plus Pe1 equals Ke2 plus Pe2. That's what we're leading into here. But if we have a non-conservative force, say, again, I'm going to go back to the car. It's always good for energy there. If my engine's applying force, then Ke1 plus Pe1 is not going to be equal to Ke2 plus Pe2, because potential energy, if you're just driving down the road, it's going to be zero each time because there's no height there. So what you would end up having is your Ke1 and Ke2 would not be equal, but up to now, we don't have a way to account for that. Now we do, because we're going to add in our work due to non-conservative forces there. And that basically represents what is happening in this little equal sign, basically, between point 1 and point 2. Well, why do we put it over here then? Well, imagine this. The Ke1, Pe1, that's before the car accelerates. If I'm adding the work of the engine, that's going to be accounted for over here. So if I add it over to the left side, that's going to account for that difference over here on the right side. This is a setup that Mr. Milligan has in his classroom that is kind of part of these, and I'm going to go through these, but I'm going to leave it up to you to kind of solve this, although I have posted the work for this on Canvas. So what is the most hazardous part on this track? Well, and these are kind of, the height in relation to the table, distance from point A on the track, and then the radius of the curve at each point. Well, what's the most hazardous? Where are you most likely to fall? Well, yeah, it's obviously part C. So at that point, we have 33.6 centimeters, a distance of 122 centimeters, and a radius of 12.2. What we want to do from this is determine the speed and centripetal acceleration if we have a force of friction between the car and the track of 0.0428 newtons and a mass of the car of 57.2 grams. I'm going to uncover this in a second, but to solve this, basically you have to look at this in terms of remembering, kind of like with the skate park sim, where your kinetic energy and your potential energy are going to equal your total energy. If you lose potential energy, you gain kinetic energy. That, as I mentioned in the previous video, this is kind of what roller coasters are built upon. I'm going to go ahead and show you that result. This is what you should get. Try to work on that on your own, but like I said, I've posted the solution to that on Canvas, so you can check that out on your own as well. So really quickly, let's take a look at, there's a bunch of problems, basically about 10 through 22, I think, that cover this whole section. So I've chosen 15 as kind of a representative sample here. So a car with mass 1,400 kilograms and initial speed 35 meters per second brakes and comes to a complete stop in 150 meters. Hey, that sounds familiar. It sounds like some stuff we did in kinematics. But we're going to look at this in terms of energy because we're looking at the amount of friction involved here. So, what I've done is I've kind of set this up in a diagram. We always want to list my knowns. So I've got mass, I've got initial speed of 35 meters per second. Because it says we're coming to a complete stop, we know our final velocity is 0, and our distance covered is 150 meters, and we're assuming a straight path for this. So I want to approach this in terms, and I'm going to actually approach this from several different ways. I'm going to start by looking at this newest formula that we learned. So non-conservative work plus K1 plus P1, K2 plus P2. So first thing I can do to solve this is go ahead and solve for my initial kinetic energy. And that's going to be 857,500 joules. My final kinetic energy is 0 because we're at a stop. And as I mentioned earlier, since we're dealing with a car, we don't have any potential energy because we don't have any height. How I can solve for this is setting this up and just plugging some values in. So my KE1 is 857,500. Everything else is 0. So that just quick algebra means that our non-conservative workforce must be negative 857,500 joules. What could that be? Well, that's the friction due to the braking of the car. So my work is equal, so I can just go back to my work equals FD formula, knowing that my F in this is my friction force due to the braking that's occurring over 150 meters. So I get a frictional force of about negative 5716.2. I'm going to round that off to 5,700 newtons for sig figs. Now that's one way I could solve that. Here's another way. Yes, we could actually use kinematics to do this as well. How cool is that? I could use VF squared equals VI squared plus 2AD to solve for the acceleration, which is negative, which makes sense because our car is slowing down. And then just use F equals ma, and F is a friction force with a mass of 1,400, and look at that. We get the same exact answer. And then another way I could look at this is by using the work energy theorem as well. I can do that very similar to before. Solve for KE1 here, 857,500 joules. And instead of putting it into the larger formula like up here, I could just kind of go straight to the point and realizing that, work energy theorem tells me that my change in kinetic energy is equal to my net work. Well, my net work, what's the only thing doing work here? It's the friction force. And that friction force is happening over a distance. So my change in kinetic energy, I went from 857,000 to 0. So that's my change in kinetic energy. And then my distance is 150. So again, solving for my frictional force, I get the same thing. So several different ways that you can approach problems like this. So just let me know if you have any questions here, and I will keep posting. Bye.